Hello, everybody. My name is Adam Meyers, and I'm with the Department of Industrial Engineering at Penn State, and my advisor is Dr. Hui Yang. And I'm going to talk about a project that's an important part of my PhD thesis. So this is on fault tolerance modeling of stochastic networks. So I'm going to first introduce what a stochastic network is. I'm going to talk about some of the challenges of studying such networks. I introduce our methodology for fault tolerance modeling of such networks and provide some simulation results and give concluding remarks. So a stochastic network is essentially a dynamical network where the status of the nodes or edges change over time. And so, for example, in this example, the green denotes an active node and red denotes an inactive node. And you see that those statuses are changing over time. And so this is a more general framework than what's often studied in the literature, which is a static network, a network that doesn't change in time. And it's also more realistic because most real-world networks are going to be dynamical, right? They're going to change in time. It's unlikely that a network in real life will remain static across its entire lifetime. So some real-world examples of stochastic networks in the top row. We have the motivating example for these, for studying these networks, and that's our body sensor network. And the body sensor network can collect physiological measurements of the body. So for example, in the top left, that's collecting electrical potentials of the heart. You're placing electrodes on the body, and it's collecting that information. On the right-hand side are the actual wearable body sensor networks. And these are stochastic networks because, for example, so these electrodes, these sensors that are placed on the body are not invasive, they're just attached to the body, they adhere to it. And so whenever the patient moves over time, they can lose contact with the patient's skin. And so, for example, the data could be incomplete, and you can consider incomplete data to be a failure. And so the statuses of those nodes are changing over time. In the bottom left, you have an example of the internet, or a local area network, where the computers or other devices are the nodes, and those can be attacked, and they can be active and inactive over time. In the bottom right, you have the brain network. So this is a brain that's undergoing an epileptic seizure, and whenever they undergo seizures, the edges connecting the different areas of the brain change over time. So new edges can be created, old edges can be deleted, and their statuses can change over time. So our goal in this project is to come up with a fault tolerance model of such networks. And fault tolerance is critical, of course, for any network, not just stochastic networks. Because we want the network to function as it's supposed to. And so some key challenges in studying these networks and coming up with the fault tolerance model. The first one is, how do we model the dynamical behavior of the nodes? So this will essentially be governed by differential equations. And for this, I'm going to propose a Markov chain specifically. The second one is, how is a network failure defined? So I'll point out here that we don't have any particular application in mind. We want to study networks in general. And so we want to come up with a general network failure criterion. And so if we were to study paths in the network, for example, studying paths in the network can lead to combinatorial explosion. So that would limit how large of a network we can study. And it also has the additional complication of the stochasticity of the network, where the nodes are changing over time, which means that the topology is changing over time. And so that'll make enumerating paths even more difficult. So instead, we're going to circumvent the combinatorial explosion problem and use percolation theory. And percolation theory has its roots in statistical physics. It moved over to network science for network robustness. And now it's just recently been of interest in the reliability engineering discipline related to our type of work. The third question is how to extract network resilience measures. And for this, again, we're going to use the Markov chain. It'll provide an easy way to do that. So you might not be familiar with percolation theory, so I want to give you some background on that. So percolation theory deals with the giant component in a network. So a giant component is, or in a finite network, the largest component. We want the largest component to contain most of the nodes, because that means that most of the nodes then can communicate with each other. And so the percolation threshold marks the percolation theory gives a very strict threshold where, as you remove nodes from the network, the largest component significantly fragments in size, or the network significantly fragments. So the largest component goes from containing most of the nodes to a network that is significantly fragmented, and you have pockets of nodes that can't communicate with one another. So an illustration of this is this video. And we start with an Erdős-Renyi random graph on 500 nodes with average degree 4. And this is subject to uniform node removal. So this particular video is showing nodes being removed 5 at a time. And the blue nodes are the nodes belonging to the largest component. Red nodes are belonging to the second largest component. And you'll see right there, actually, that the second largest component peaked in size, and that's critical. And you see that the network continues to be significantly fragmented, whereas in the beginning, if you remember, you had a large component containing most of the nodes. So this percolation threshold is very convenient because it'll give us a natural failure criterion of a network and also allow us to circumvent combinatorial explosion. In other words, we can study large networks. And the right-hand side shows graphical forms of what's happening on the left. This graph right here shows the size of the second largest component, and it's showing it shows that the second largest component increases, and then it peaks, and then it decreases. So this peak is particularly important because the peak of the second largest component, the peak of its size, marks the percolation threshold. So we can determine that at this time, roughly time 5, the network significantly fragmented, and the network reached its failure state. So a problem with with using percolation theory is that it suffers from a finite size effect. And this is relevant because all real-world networks are finite, and we want our methodology to apply to real-world networks. So we're going to take this effect into account in our methodology. So the finite percolation threshold you see on the left-hand side, it varies for a finite network. The red dots mark the average percolation threshold that's simulated. So these are over across maybe 1,000 simulations. You simulate an Erdős-Renyi random graph 1,000 times. You iteratively remove the nodes, and then you determine based off of the peak of the second largest component when the percolation threshold occurred, what the number is. And this is showing the average of those, the red dots. And I think this is one standard deviation way. So this also shows the variation. So the finite percolation threshold varies because each time we generate a new Erdős-Renyi random graph, we have a different graph with a different topology. We may have the same number of nodes, but we have a different topology, and we remove the nodes in a different way, right? So we can randomly remove them, but that's going to change from iteration to iteration. So the percolation threshold is going to vary for a finite network. And this black line marks the infinite percolation threshold. So this is the threshold for an infinite network, which is a constant. For an infinite Erdős-Renyi random graph, for example, with an average degree of 4, the percolation threshold is 0.25, which is what this shows. And the finite percolation threshold approaches that in the limit. And the variation you can see decreases as well as you increase m. So we're going to simulate this using the idea before, taking the peak of the second largest component. So this is again over many iterations. So this is the average size of the second largest component. So each realization would generate one of these curves. We average those curves together to get the blue curve. And so the standard in the literature is to just take the maximum of the blue curve, but we're going to propose to fit a curve to the blue curve, and then take the peak of that, and that'll be used to form the estimate of the percolation threshold. And the reason for this is because we know how the finite percolation threshold scales. We know how it approaches the infinite percolation threshold, like in this case, 0.25. We know how it scales for Erdős-Renyi random graph, and we can use that relationship to test whether or not we're getting accurate numbers for the finite percolation threshold. And it turns out that I used both of these methods, and the fitted curve ended up providing more accurate finite percolation threshold approximations. Okay, so now onto the continuous time Markov chain. Again, this is going to model the node behavior, the dynamical node behavior, and also allows us to compute resilience measures. So at a higher level, the network level, the Markov chain is defined, the state of the Markov chain is defined to be the number of active nodes. So that'll range from 0 to n, we have n nodes. Each node is equipped with a failure time that's exponentially distributed with a mean of lambda, and a recovery time that's also exponentially distributed with a mean of mu. So this rate diagram shows the Markov chain. If we're in state I, that means I nodes are active. If we want one more node to be active, then we need the current n minus I failed nodes to recover, right? So times the recovery rate. And similarly to go from state I to I minus 1. At a node level, so at a network level or at this higher level, this is just a birth-death process. At the node level, we have a simple on-off process for each node. Okay, once we have this model in place, we can then compute resilience measures. So since we're using the percolation threshold as the criterion for the network failure, the percolation threshold really gives us how many nodes must fail before the network breaks down. So from a fault tolerance perspective, this leads to a couple questions. Specifically, when is the network expected to reach this critical number of nodes that will break down the network? And how often is the network expected to be in a working condition? So these are the two questions we're going to focus on when we're, for our motivation for the resilience measures we compute. So for the first question, again, when is the network expected to reach the critical number? That's just the mean time to first failure. Right. So the mean time to first failure is just summing up the, before I say that, here's the failure state of the network, right? So this is based off of PCN is the finite percolation threshold, times n, take the floor, that gives us an integer. So remember the states of our Markov chain are integers. So whenever we reach this number of active nodes, this number of nodes that are active, then the network is considered failed. If we have any number above that, so +1 and above, then the network's considered up and running. So to get the mean time to first network failure, we just have to sum up the expected time to go from each state, right? Until we get to the failure state. So that's what this is showing. To complete this, this is incomplete. I didn't show it, but you need to derive recursive equations, and then you can easily compute this. Similarly, if we can compute the mean time to first network failure, we can also compute the variance of that time. And that's what this is. It's very similar. You're summing up variances. For the second question, how often is the network expected to be in working condition? Well, that's another way of saying the availability of the network. So we'll compute both the transient and steady state. The transient availability is just what's the probability that the network is available at time t. So we've derived it as such. Again, you have the failure state here. And here's the formulation. Again, mu is the recovery rate, and mu is the recovery rate, and lambda is the failure rate. If you take the limit of this as t goes to infinity, you can get the steady state availability of the network, which is sometimes more useful. Okay, so we did some simulation results on Erdős-Renyi random graphs. We also did a case study. I didn't include it here in the interest of time. But for the Erdős-Renyi random graph, we have the parameters are the number of nodes n, so that's 100, 1,000, 10,000, and the average degree of the network, 1.5, ranging from 1.5 up to 5. So if we have an average degree of 5, that means we have a lot more edges. If we have an average degree of 1.5, we have a lot less edges. The network is a lot sparser. So this is showing the mean time to failure as a function of gamma. So this is the ratio of recovery rate to failure rate. Right? So if we're above 1, that means that nodes are recovering faster than they're failing. If it's below 1, that means nodes are failing faster than they're recovering. So what we can see from this is that, as expected, as we increase the gamma, so as we increase the recovery rate relative to the failure rate, it takes a longer time for the network to fail, right? MTTFF is increasing. Another thing that we would expect is that networks with higher average degree are more robust, so they're going to take a longer time for them to fail. These graphs also show that. The last thing these graphs show is that as you increase the network size, you actually get more robustness of the network. And so that's a little odd, but the reason that that's occurring is because we're using the percolation threshold. So the percolation threshold in our previous example was, say, 25%. So whenever we reach 25% of active nodes, then the network fails. But the finite percolation threshold is usually above that. So that could be 30%. Say we have a network on 1,000 nodes, and we compute the finite percolation threshold to be 30% active nodes. Well, it takes a shorter time to reach 30% active nodes than it does to reach 25% active nodes, right? Less nodes have to fail. So what that translates into is that infinite networks will be more robust, but that's more of a just a side effect of percolation. Another result, this concerns question number 2, how often is the network expected to be in working condition? So the availability. This is just showing the availability at time t, right, as we expect approaches. So at time 0, right, all nodes are active, so its availability is 100%, but it decreases over time and approaches steady state. The other thing that we show is the steady state availability, right, so A. And we're now showing it as it's no longer a function of time, it's steady state. So we're showing it as a function of gamma, the parameters, right, the ratio of recovery to failure. And we have it for different sizes of networks. So this is 100, going from right to left, 100, 500, 1,000. And we see that as gamma increases, so as the recovery rate increases relative to failure, we get more steady state availability, right? The availability comes closer to 100%. Another thing that this shows is that as we increase n, steady state availability seems to approach a step function. And this makes sense because the percolation threshold in the infinite case is a clear cutoff, right? It's a strict cutoff that's, say, 25% nodes. That's clear, it's not oscillating at all, it's a strict cutoff. And so it makes sense that either the network's available or it's not available in the infinite case. In the finite case, we don't have that because of the finite size effect. And we're concerned with finite networks, real-world networks. The last thing that I'll point out from these simulation results is the finite size effect. And we can see it more clearly here. So say take 100 nodes, and this is the mean time to failure again as a function of recovery to failure. Sorry. And what we can see then, so the right-hand curve represents PCN, the finite percolation threshold, and the left-hand curve represents the infinite percolation threshold. So a way we can look at this is if we hold gamma constant, right? So say gamma is at 0.3 here, then the network's going to fail sooner, right? The mean time to failure is smaller than it is for the infinite case, right? If we use the infinite percolation threshold as the failure criterion, we get a larger mean time to failure. So we would incorrectly surmise from this that our network is more robust than it actually is. And so this is important, again, because all real-world networks are finite, and because, you know, the literature, I haven't really seen many people use, if any, I haven't really seen any papers that have used the finite percolation threshold as the failure criterion. So the reliability engineering papers that use percolation theory. I have not really seen ones that use the finite percolation threshold. They use the infinite one, even though they have a finite network, and that's going to lead to erroneous conclusions, erroneous results. So we consider that in our framework. So just to conclude, stochastic networks are more general, right? We're not just considering static networks. They're more realistic, as I've pointed out many times. Fault tolerance is crucial. That's what we're studying in this presentation. And I've proposed Markov chains to model node failures and recoveries, the dynamical behavior of the nodes. It also allows us to compute resilience measures. We've used the percolation threshold as our general criterion for network failure. And our contributions, we've proposed this framework, we've considered the finite size effect, and we're one of the few papers who considers percolation with node recoveries. Most percolation has been done on static networks. So here's our contact information. Feel free to contact me or my advisor, and thank you very much for your time.